Assalamualaikum and salam sejahtera. Welcome back to Cikgu Zana channel. Hope all of my students are doing well and are prepared for today's lesson, which is on application of integration, finding the area of planes, part 1. Part 2 will be published shortly. So for those who are new here, don't forget, please subscribe. So students, stay focused and let's start.
By the end of this video, it is hoped that students should be able to calculate the area of region between a curve and the x-axis, area of region between a curve and the y-axis. Let's look on how to find the area of a region between a curve and the x-axis. Consider the region bounded by the curve y equal f of x and the lines x equal a and x equal b and the x-axis. The area of the bounded region is found by integrating y equal f of x between the limits of a and b. In other words, the area A is obtained by evaluating the definite integral of y from x equal a to x equal b. Key points. When the integral has a positive value, it indicates that the bounded area is above the x-axis. When the integral has a negative value, it indicates that the bounded area is below the x-axis. Thus, the positive and negative values of the integral help us to identify where the regions lie. Remember, area is a scalar quantity, so the values of area must always be positive. Let's look at the first example. Part A, sketch the curve of y equal x squared times 3 minus x. Part B, find the area of the region bounded by the curve and the x-axis. Remember the steps to be taken in curve sketching. First, we need to identify the shape. Okay, since the curve y equal 3x squared minus x cubed, I have already explained it. It's a cubic curve where the coefficient of x cubed is negative. Then the shape of the curve starts from the left and goes to the right. Next, find the point where it touches or cuts the y-axis and the x-axis. So when y equals 0, x is 0 and x equal 3. Thus, the curve passes through 0, 0 and 3, 0. Next, find the maximum or minimum point if any. So first, find the turning point. At turning point, dy dx is 0. dy dx is 6x minus 3x squared. Factorizing it, we have x equals 0 and x equals 2. When x equals 0, y is 0. When x equals 2, y is 4. Next, find the second derivative. We have 6 minus 6x. So at the point 2, 4, d2y dx2 is negative 6, which is less than 0. Thus, 2, 4 is a maximum point. At the point 0, 0, d2y dx2 is 6, which is positive. Then the point is a minimum point. Now let's sketch the curve. First, plot the x-axis, followed by the y-axis. Then, sketch the curve and label the points. Notice that the curve passes through 0, 0 is a minimum point, 2, 4 is a maximum point, and the curve cuts at 3, 0. Now shade the region where it is bounded by the curve, the x-axis, from x equals 0 to x equals 3. Thus, the area of the region is the definite integral of y from x equals 0 to x equals 3. Substitute y, 3x squared minus x cubed. Integrating, we have x cubed minus x to the power of 4 divided by 4. Next, substitute the upper limits into the integral. So we have 3 cubed minus 3 to the power of 4 divided by 4. And substitute the lower limit x equals 0. So we have minus 0. Evaluating, the area is 3/4 units squared. Example 2. Find the area bounded by the curve y equal x cubed minus 4x squared plus 3x and the x-axis from x equals 0 to x equals 3. First, we sketch the curve, and notice that the curve is a cubic curve with coefficient of x cubed is 1. Thus, the shape of the curve is a cubic curve that starts from the right and goes to the left. Next, find the point where it cuts the x-axis. When the curve cuts the x-axis, y is 0. Factorizing, thus the curve cuts the x-axis at x equals 0, x equals 1, and x equals 3. Now, we are not required to find the maximum or minimum point, since the curve is sketched as a guide to identify the regions. So plot the y-axis and the x-axis and plot the curve. Notice that the region is bounded by the curve and the x-axis. 1 is on top of the axis, so we label as A1, and the region that is below the x-axis we label as A2. To find A1, we integrate the function from x equals 0 to x equals 1. Thus, integrating, we have x to the power 4 divided by 4 minus 4x cubed divided by 3 plus 3x squared divided by 2. Substituting the upper limits x equals 1, we have 1 over 4 minus 4 over 3 plus 3 over 2. Now, when we substitute the lower limit x equals 0, the value is 0. Thus, we do not need to write 0. Evaluating, A1 is 5 over 12. Next, to find A2, we integrate the function from x equals 1 to x equals 3. Integrating, we have the same integral. Substitute x equals 3, the upper limits. We have 81 over 4 minus 36 plus 27 over 2. Minus, substituting the lower limits x equals 1, we have 5 over 12. Evaluating, A2 is a negative 8 over 3. Remember, the negative sign is to indicate that the region lies below the x-axis. Hence, the required area is A1 plus the positive value of A2. Remember, area is a scalar quantity, so it must take a positive value. Adding the two areas, we have 37 over 12 units squared. In example 3, we are required to sketch on the same coordinate axis the curve y equals ln x minus 2 and the straight line x equals 4. Calculate the area of the region bounded by the curve y equals ln x minus 2, the straight line x equals 4, and the x-axis. To sketch the curve y ln x minus 2, Let's recall the shape of a logarithmic curve. It is an arc. The asymptote of the curve is x equal 2, because when x equal to ln 0 is undefined, meaning that the curve will never cut the line x equal 2. When x equal 3, y is ln 1, ln 1 is 0. Thus, the curve cuts the x-axis at x equal 3. Next, we plot the y-axis, the x-axis, the asymptote x equal 2, and the curve that passes through x equal 3, and lastly, the line x equal 4. Firstly, we identify the region that is bounded by the curve, the line x equal 4, and the x-axis. So we have, thus the area is the integral of the function ln x minus 2 from x equal 3 to x equal 4. Since the function is a logarithmic function, we have to use the integration by parts method. So let u be ln x minus 2. Differentiating, we have 1 over x minus 2. Let dv dx be 1. Integrating, we have v equal x. Substitute into the formula. We have u ln x minus 2 times vx minus the integral of v times du dx with respect to dx from x equal 3 to x equal 4. Substituting the upper limits, we have 4 ln 2 minus, substituting the lower limits, x equal 3, we have 3 ln 1, minus the integral of 1 plus 2 over x minus 2. Since the integral of x over x minus 2 is an improper fraction, so convert it to proper fraction, we have 1 plus 2 over x minus 2. So we have 4 ln 2, 3 ln 1 is 0, minus the integral of 1 is x. The integral of 2 over x minus 2 is 2 ln x minus 2. Remember, we can take the constant 2 outside, integral of 1 over x minus 2, and since this is of the form f prime x over f of x, thus we have 2 ln x minus 2. Substituting the upper limits and the lower limits, we have 4 ln 2 minus 4 plus 2 ln 2 minus 3 plus 2 ln 1. Simplifying, 4 ln 2 minus 2 ln 2 is 2 ln 2, minus 4 plus 3 is minus 1. Now we can leave our answer in terms of ln. To find the area of a region bounded by the curve x equal f of y, the y-axis and the line y equal a and y equal b is given by a equals the definite integral of x from y equal a to y equal b. Key point: when the integral has a positive value, it indicates that the bounded area is on the right of the y-axis. When the integral has a negative value, it indicates that the bounded area is on the left of the y-axis. Remember, area is a scalar quantity. It must take a positive value. The negative sign is just to indicate where the region lies. Let's look at the first example involving area between a curve and the y-axis. Find the area of the region bounded by the curve y squared equal 3x, the lines y equal 2, y equal 5, and the y-axis. Now, it is encouraged to sketch the curve y squared equal 3x to identify the area of the required region. Next, convert x in terms of y. So from y squared equal 3x, we have x equal y squared over 3. Thus, the area of the bounded region is the definite integral of x from y equal 2 to y equal 5. Substituting x in terms of y, so we have y squared over 3, integrating, simplifying, substituting the upper limits y equal 5, we have 5 cubed, minus, substituting the lower limits y equal 2, we have 2 cubed. Simplifying, we have the area equals to 13 units squared. Second example, find the area of the region bounded by the curve y equal 2 times e to the power of x, the y-axis, and the lines y equal 1 and y equal 4. It is best to sketch the curve as a guide to where the region lies. E to the power of x is an exponential curve, where the value of the exponent x is positive. Thus, the curve is an arc that cuts the y-axis at y equal 2. Next, identify the region bounded by the curve, the line y equal 1 and y equal 4. Thus, we have. Observe that the bounded areas, one is to the right of the y-axis and the other is to the left of the y-axis. Now, label the region on the left side of the y-axis as A1 and the region on the right side of the y-axis as A2. Next, from y equal 2 times e to the power of x, we convert it as x in terms of y. So the area A1 is the integral of the function ln y over 2 from y equal 1 to y equal 2. Since the function is a logarithmic function, hence we have to apply the integration by parts method. So letting u as ln y over 2, differentiating, we have 1 over y, and letting dv dy as 1, integrating, we have v equals y. Substitute into the formula, u ln y over 2 times vy minus the integral of v times du dy. So we have, substitute the upper limits, we have 2 ln 2 over 2 is 1 minus ln 1 over 2 minus the integral of 1 from y equal 1 to y equal 2. Integrating, 1 we have y, simplifying, 2 ln 1 minus ln 1 minus ln 2. This is done by applying the logarithmic rules of quotient. Thus, we have ln 2 minus substituting the upper limits, which is 2, minus the lower limit, which is 1. Thus, A1 is ln 2 minus 1. To find the area of A2, we integrate the same function ln y over 2. The only difference are the limits, that is from y equal 2 to y equal 4. Thus, integrating, we use the same integral as a1. We have y ln y over 2 minus the integral of 1 from y equal 2 to y equal 4. Substituting the upper limits y equal 4, we have 4 ln 2 minus, substituting the lower limits y equal 2, we have 2 ln 1 minus, the integral of 1 is y. Hence, simplifying, 4 ln 2 minus 2 ln 1 is 4 ln 2 minus, substituting the upper limits which is 4 minus the lower limit which is 2. Thus, a2 is 4 ln 2 minus 2. Hence, the total area of the region is the modulus of a1 plus a2. Remember, area takes a positive value since a1 is on the left side of the y-axis. So, we have the modulus of ln 2 minus 1 plus a2, which is 4 ln 2 minus 2. Now, ln 2 minus 1 is actually a negative value, negative 0.30685, hence the modulus sign. So we have 1 minus ln 2 plus 4 ln 2 minus 2. Simplifying, we have 3 ln 2 minus 1 units squared. Okay, you can leave your answer in terms of ln or in terms of decimal values, which is 1.079 units squared round off to 4 significant figure. For the last example, we are required to calculate the area of the region bounded by the curve y squared equal x, the straight lines y equal negative 1, y equal 3, and the y-axis. So first, sketch the graph of y squared equal x, which is a quadratic curve symmetrical at the x-axis. Draw the lines y equal negative 1 and y equal 3 to identify the regions. Label the regions as A1 and A2. Observe that both the regions lie on the right side of the y-axis. So both the integrals have positive values. Thus, the area of the region is the sum of A1 and A2. A1 is obtained by integrating x from y equals negative 1 to y equals 0, and A2 is obtained by integrating x from y equals 0 to y equals 3. We can simplify the integral by applying the following rule of integration. Thus, the integral of x from y negative 1 to y 3 is the integral of y squared from y negative 1 to y 3. So integrating y squared, we have y cubed over 3. Substituting the upper limits, 3 to the power of 3, which is 27, divided by 3, we have 9, minus, substitute the lower limit, negative 1, we have negative 1 over 3. Thus, the sum of the area is 9 1 over 3 units squared. Summary for today's lesson. To find the area of region bounded by a curve, the x-axis lines x equal a and x equal b is given by the definite integral of f of x from x equal a to x equal b. To find the area of region bounded by a curve, the y-axis lines y equal a and y equal b is given by the definite integral of f of y from y equal a to y equal b.
That's about all. So I end this lesson with the saying, practice makes perfect. Please do visit my channel for more video lessons. Till then, bye for now and see you again in my next video.